Hello everyone and welcome to Dynamics Lectures. In this lecture, we will solve a relatively simple problem shown over here. The purpose of this problem is to obtain better understanding of the equations describing the motion and rotation of a rigid body about the fixed axis. Here is the problem formulation. A rope is wrapped around the wheel. The rope is pulled with a force that produces the constant acceleration denoted by A. If the radius of the wheel is r, determine A. Angular acceleration of the wheel, B. Angular velocity of the wheel, and C. Rotational angle of the wheel. But before I solve this problem, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 300 video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start. Since the acceleration of the rope is in this direction, the wheel will rotate like this. And theta is the angle of rotation. For example, if initially the point of the wheel was here, and let this point be denoted by A, after some time, this point will go over here, and the angle will be theta. This is the rotational angle. So let's analyze what's happening over here. In my previous lecture, whose link is given in the description below this tutorial, I derived the expressions for the angular acceleration, angular velocity, as well as for the acceleration and velocity of a rigid body rotating about the fixed axis. And one of the main conclusions is that the acceleration vector, denoted by A, has two components. It has a normal component and it has a tangential component. For this problem, the most important is the tangential component. From the problem description and the fact that this acceleration is always oriented downwards, we conclude that AT is equal to A. That is, the intensity of the tangential acceleration of this point A is equal to A. On the other hand, in my previous lecture, I shown that AT is actually equal to the radius of the trajectory, r, times alpha, where alpha is the angular acceleration. Now, since A is given, we can write this equation as r times alpha is given as A. This is the very important equation. From this equation, we can express alpha, that is our angular acceleration of the wheel, as A over r. And we solve number A. Let's solve the problem B. We need to compute the angular velocity of the wheel. The angular velocity is usually denoted either by omega or theta dot. There is a nice relationship between alpha and omega. Alpha is simply the first derivative of omega. That is, the angular acceleration is the first derivative of the angular velocity. And if you use theta dot, this equation will look like this. Derivative of theta dot, and that's the second derivative of theta. To compute omega, we need to integrate this equation. Consequently, we obtain the following. d omega is alpha times dt. And from this equation, omega is an integral alpha times dt plus some constant c0 that's determined from the initial condition. Let's solve this equation. Now, Since alpha is constant and it's equal a over r, we can simply substitute this expression. So we have a over r dt plus c0. And we obtain omega as the function of time. Omega as the function of time is equal to a over r. A over r is constant. And over here we have time, since we have 1 times dt, and that's simply equal to t plus c0. Good. We need to determine the c0. Here we will assume that the wheel starts from initial angular velocity equal to 0, and consequently c0 will be equal to 0. Let's show that v of 0 should be equal to 0, so we have 1 a actually over r times 0 plus c0 should be equal to 0, and from here we obtain c0 is equal to 0. And omega as the function of time is simply a over r times t. In order to make this video tutorial as clear as possible, over here I wrote the solution of the problem B. We will need this solution in order to solve the problem C. Let's solve the problem C. We need to compute the rotational angle. That is, we need to find a function that describes rotational angle as a function of time. How to do that? Well, we know that omega is actually equal to the first derivative of theta. From this equation, we obtain that d theta is omega times dt. Let us integrate this equation. By integrating this equation, we obtain that theta is equal to the integral omega times dt plus some constant. Let's denote this constant by c1. In this expression, we will substitute the solution of the problem B, and consequently we will obtain that theta is an integral of a over r t times dt plus c1. From the last equation, we can obtain the following. A over r is simply a constant and can get out of the integral, and in integral we have t dt plus c1. From this expression, we obtain that theta is actually equal to a over r t squared over 2 plus c1. Here, in order to find c1, we need to assume a certain initial condition. I assume that initially theta is equal to 0. Consequently, we have theta of 0 is equal to 0. Let's substitute this initial condition over here in order to find c1. We have 0 is equal to a over r multiplying 0 squared over 2 plus c1. From this equation, we obtain that c1 is equal to 0, and consequently theta is equal to a over r theta squared over 2. Perfect. So how can we verify that this solution is correct? Well, this is easy. If we take the first derivative of theta, we should obtain omega. So let's see that. Theta dot is obviously equal to, let's see, a over r, and what do we have over here? 2t over 2, that's simply t. Perfect, and that's exactly this expression. Now, we can also verify the solution to the problem A. How to do that? We know that alpha, that is the angular acceleration, is the second derivative of theta. Consequently, we obtain theta 2 dot is a over r, and that's precisely alpha. That's perfect. Okay, that would be all for today. I hope that you liked this video. If you like the videos I create, please press the like and subscribe buttons. Thanks a lot and have a nice day.